Okay, so there's two words on this slide that I need you to understand. And so yesterday we talked about how atoms exist in quantized states, and what that means is that they can only exist in certain levels. Okay, so what is that thing that is a specific amount of energy that can be gained or lost? A quantum. Okay, and what is a quantum travel inside of? A photon, and a photon is just simply just this ball of light. Okay, so today we need to talk about how those electrons can be moved up and down. Okay, so the lowest energy state of an atom is called the ground state. Make sure you know those two connected. So imagine if we were to step right outside this window, what would we be standing on? The ground, and this is a very low energy state. You need zero energy required to stand on the ground. Okay, when a state in which an atom has a higher potential energy than it has in its ground state, it is called an excited state. But let me ask you something. How do we get it to an excited state? Thank you. It must absorb energy. Absorb energy. So if I took you outside and I said, hey, I need you to get to the roof. But you didn't have a ladder and you didn't have stairs, how could you get there? But you need a lot of energy, right? A whole lot of energy. Imagine if I handed you a Red Bull, what would it give you? Wings. That's a joke. Okay. So it could get you to the roof. So you would have to absorb some energy from the ground state in order to get to a higher excited energy state. So what does that mean? What does all this have to do with? So how does this apply, and how do they figure all this stuff out? So we're actually going to do this lab. It'll probably, honestly, be after Christmas when we get back, just because of time's sake. But it's a really cool lab, and I want you guys to be able to see it. So this is what they did. They used the hydrogen atom line emission spectrum. That's a lot, and we'll kind of talk about what each part means in just a second to figure some of this stuff out. So what they did is when investigators passed an electric current. Now, what is an electric current? It is, but it's nothing more than the flow of electrons, okay? Through a vacuum tube. Now, when I say vacuum, I don't mean this little thing, the Hoover that sucks dirt off the carpet, okay? In a vacuum, what I mean is this: it is a container that contains nothing. I know that sounds weird, but when I say nothing, all of the gas molecules, all of the particles that are in that tube have been sucked out. So literally there is nothingness in there. It's like the middle of space. There's no air, there's nothing, so you could not breathe. But what they did is they took that tube and they filled it with hydrogen gas. Now, out to the left of the hydrogen gas, I want you to write this down. The formula for hydrogen gas is H2. Let me actually write it right here so you guys can see it. H2. What do we call those things that are found in pairs? Very good. Diatomics. Okay, so remember how many there are? There are 7 of them. We've only talked about 3, but there are 7. We'll get to who they are later on. Okay, so they filled this hydrogen gas, and they filled this tube with hydrogen gas, and only hydrogen gas, and they ran an electric current through it. And then they observed. Now, what do you have to use to observe? Your eyeballs. Now, some of you need glasses, but you use your eyes. But you've got to remember, do our eyes perceive things as they truly are? No, it's basically only what we can see. So they observed the emission. What does emission mean? To give off. So they observed the emission of a pinkish glow. That is a very important point to this. A pinkish glow. Up to this point, thinking back to the electromagnetic spectrum, why should that be very weird? Very good. Roy G. Boo has no pink in it. So how are they seeing pink? It's a mixture of colors. And so they said, okay, well, this gas must be giving off more than one part of the spectrum, which is the reason we see it as pink, is because it has a mixture of colors. So this is what they did. They took that pinkish glow and they shot a narrow beam of it through a prism. And what does a prism do? It separates it out. And this is what they noticed. It's separated into 4 specific colors. Know that number. 4 specific colors. Now, the picture you're going to see in just a second, the slide right after this, there's a little white lie. And here's why it's a little white lie. There are technically 5 that it breaks into. But one of them is out of the visible range, which means what? You can't see it, okay? But it's there, you just can't see it with your eyes. So when you see the picture in a second, you're going to see 5 of them. But what do we know about one of them? You can't see it, but they show it anyways. So the hydrogen gas turned pink, and it's separated into 4 specific colors. And what they said is the visible spectrum of the 4 bands of light were part of what is known as hydrogen's line emission spectrum. Now, this is going to make sense when you see the picture, but we know emission means what? To give off, and what is it giving off in the spectrum? Lines. Well, let's look at the picture and let's see if it makes sense. Well, how about that? Okay, there's a bunch of lines. So let's start over here on the far left. What color is this glowing thing? It's pink. This is what they saw. They put it through a slit, then they sent it through a prism, and it split into these, what we see is 5 bands. However, this one right here is in the non-visible range. Can someone tell me what range it's possibly in? Very good. How do you know it's in the UV range? It's a violet color, and it has that value, okay? So that's how we know that it's in that. And again, I'm not requiring you to know the ranges, but that's what it is. So because of this issue, they were able to determine exactly what types of frequencies that the hydrogen gas gives off. Okay? So this is hydrogen's line emission spectrum. So here's the purpose of the lab whenever we do it. We're going to do hydrogen, helium, argon, neon, and I think carbon dioxide. I can't remember what all comes in the kit because they have to deliver it to me. But here's what we're going to see. The first question I have is, do you think all of the gases to the naked eye glow the same color, such as do they all glow pink? No, they don't all glow pink. So if that's the case, if they don't all glow the same color, will they produce the same line emission spectrum? No, and that's the purpose of the lab. What we're going to be able to do is to determine the line emission spectrum for all those different gases. And they're all going to be different. Well, I know what you're saying. Well, why do we care? Why do we want to look at all those things? What they can then do is, and we're not going to do this, but scientifically what they can do is they can take a tube of an unknown gas. And if they have all these pictures stored in Google, because I know that's how y'all think about stuff, if they take the spectrum of an unknown gas, can they compare it to all the ones in Google and figure out what the gas is? That's the purpose of it. Okay? So it allows them to find out what the unknown is by comparing it to all the other knowns. Yeah, and you could, the higher the frequency it went, the more it put off. So yeah, you could determine if it was as dangerous or not. Okay, that's a good question. All right, so then what Bohr did is he took this model and he created the Bohr model. Okay, now above this slide, I know it's already kind of written, but I want you to write at the very top of this. Now, first of all, make sure you spell his name right. It's B-O-H-R, not like the pig you shoot in the woods or like the fact that you think I'm boring. It's B-O-H-R. Bohr is, at the very top, right? Bohr is boring. Like he is boring. B-O-R-I-N-G. And what I mean by that is, guess what? Bohr was wrong. But we still got to talk about him because he developed the first model of what electrons did. So Niels Bohr proposed a hydrogen atom model that linked the atom's electrons to photo emission. Now, let's pause right there and let's talk about it. What is what is a photon? It's a ball of light, right? Okay, what's inside of that photon? A quantum. And what does emission mean? To give off. So he proposed a model that talked about how the hydrogen gives off photons of light. According to the model, the electron can circle the nucleus only in allowed paths called orbits. So the thing you need to connect is that Bohr said they traveled in a what path? What do we know of other things traveling in orbit patterns? Planets, okay? So what he said is they follow the same pattern, round and round and round they go all the time. But we know that today that Bohr was wrong. But you do need to know what he established because it was important. But this bottom bullet is the important thing, is because how he established the energy is key to what we're going to talk about in a little bit. The energy of the electron is higher when it is farther from the nucleus. So the energy is higher the farther it is from the nucleus. And let me give you a silly example of this. Spring break. You all freak out when mama's not around, don't you? I know. Y'all act real bad when nobody's watching you. I know how y'all work. Okay? So, again, the farther you get away from home, the more you can act like your typical high school self. We'll just kind of go with that. So, it took in more photons. Remember, photons contain quanta and all that good stuff. So, essentially what he was saying is that electrons have the ability to go upstairs. Okay, and every stair was a different orbit. But again, the key part is, does it require energy, Cody, to go upstairs? You sure? How much energy? That Q word. A quantum of energy to get from stair to stair. Okay? All right, so this is Bohr's proposed model of an atom. And what he basically said is that for this guy to come out here, for him to come out here, what does it require? Dude. No. What are you doing? It's constant. So for something to go out an energy level, or an orbit is what he called it, it's going to require some energy. Okay? But what happens when this electron wants to jump down here? What does it do? It releases energy. And the reason I'm drawing this is because on the next slide, we're going to talk about what these two things are, Cody. Just go ahead and move up here. Thank you. It would help if you had your notes out too. Thanks. Okay. So, what is it called when they jump these energy levels? Essentially, what are they doing when they go up and down these sets of stairs? Okay. When an electron falls to a lower energy level, a photon carrying a quantum of energy is emitted. If I were you, I'd put a big circle around this page. You're going to come back to this a lot. Okay, just put a big circle around this page. So, when it falls energy levels, it gives off a photon. And what is a photon? Please stop. Please stop. It's a ball of light. Okay? Stop. Okay. And what do we call that process when it gives it off? Emission. Okay? So, again, if you're kind of like, when it falls, it emits. When it falls, it emits. So let me give you that reference back outside. So if I take you up to the roof and push you off, which I would never do. I like you all too much to do that. I don't know, Mason. You may get the first push. So when you hit the ground and go splat, other than your bones probably snapping, what's going to happen to the energy? It's going to come out of you somehow, shape, form, or fashion. Okay, by a scream or a bone or something. But the energy is going to be released in some shape, form, or fashion. So what happens to get you to the roof? So energy must be added to go higher, and that is called absorption. So just like I said a minute ago, to get you from the ground to the roof, you've got to have some energy. So I can give you a Red Bull, there's your energy, gives you wings, and you fly to the top. So it's the same kind of concept. The two words here that are important are emission and absorption. And you knowing how those two things happen. When you emit light, you're dropping energy levels. But when you're absorbing light, you're jumping up energy levels. So did we talk about the microwave in here? Okay, perfect. So I want to make sure that we talked about that in here. Yep, in the city. So this is one picture that kind of summarizes exactly what we just talked about. So the ground state versus the excited state. So it involves energy input or release. So if we have emission, now emission means to do what? All right, so emission means to give off. And what happens to the electron? Does it drop or does it go up? Okay, and so it goes down And I'm going to write the abbreviation EL, and we'll come back to that. But EL, if you're one of those you want to write the whole thing out, EL stands for energy level. Energy level. So in emission, it gives it off, it goes down. Okay? So the opposite effect, and I don't like the way this is written. It's not exactly right. So when energy comes in, it absorbs it. They call it excitation. I prefer absorption. Okay? Because I think about it kind of like a sponge. It just soaks it up. And notice what happens to the electron. What does it do? It goes up. It goes up in energy level. And here's what's happening. These electrons are doing this constantly, back and forth, up and down, up and down, up and down. And whenever you see the electrons giving off light, that's what's going on. So let me tie this back into what we talked about a minute ago. Did that tube of hydrogen gas, when we plugged it into the wall, start glowing? We saw it was going what color? Which process was allowing us to see that pink color? Which process? Emission. This caused the pink color. Now, we just talked about it, so let's tie it back in. We know that pink is not a real color. Don't throw anything at me, okay? Because I know that upsets a few of you. Pink is not real. So, what does that tell us about all of these photons that are given off? Are they the same photons, or are they different? They're traveling at different frequencies. Okay? So because it's pink, you have photons. This is the last part I'm going to write on the slide. You have photons. Again, what is a photon? A ball of light at different, follow my shorthand. Photons at DIFF and at different nu. And what is nu? Frequency. So you could actually say nu and lambda, frequency and wavelength, because they relate to each other. Okay. So the reason we have the pink color is because photons at different frequencies and wavelengths are being given off. That's how we were able to see the pink color. So does this tie all back in? Does all that make sense? Please ask a question if you're kind of lost at any point in this. Okay, go ahead. That's a good question, because photons are all different, and how they're given off. Yes, exactly. How the electron gives off that amount of energy can change, sir. Okay. Photon. A photon is the energy within it. Yes. Okay, is the energy within it. Very good. Any other questions? Okay, so this is just, y'all don't even think y'all have that, do you? All right, I'll delete it. It's the same exact picture we just saw. Valence shell, the only thing I want to talk about the valence shell, is where is the valence shell? Very good. It is the outermost, and again, I'm going to write this because this is technically right. What is EL? Energy level, okay? There's one last thing I want to ask about this, and I think most of you already know this, so it's not a big question. The first energy level of an atom can only hold how many electrons? 2. That is going to be a very important theme as we go throughout the rest of this chapter. The first energy level can only hold 2. And then the last thing I want to mention, so there are 3 things, I apologize. This word right here, noble gases. Where are they up there on the wall? The far right. What makes them special? Okay. They can't react. Okay. So what that means is the valence shell of the noble gases are full. Very good. Yes, sir. They are full. Except one of them. Take it back. One of them doesn't have 8. Who doesn't have 8? Look up there. Look again. Try again. Helium. Helium only has how many? I did. I agree with you, but I wanted everyone to see it. Helium only has 2. Well, it can't have 8 if it only has 2. So that is the truth about the valence shell of the noble gases. And we'll talk more about the other groups as we go along. Cody. Seriously. All right. So let's talk a little bit about how the valence shell and the nucleus react. Okay. Do me a favor. Up here at the very top, write, how do I want to write this? This is the nucleus versus the electrons. Above the slide, not where I wrote it, write it above. So this is Coulomb's force, or Coulomb's law. Okay. Someone always says it looks like Columbus, and they just did a bad job of spelling. It's called Coulomb. This is the guy's name. It is Coulomb, and here's what Coulomb's law states. The closer 2 charges are, the stronger the force between them. Duh, right? But there's one important fact about this that has to be true. What do you notice about the signs of those 2 things? It has to be opposite charges. That, bingo, that is exactly what we have to understand. So exactly what Mason said is an important point. The closer 2 magnets get, what do you notice about the attraction between them? The stronger it is. But what happens if you flip one of those magnets over? What does it start doing? It starts pushing harder and harder, and you can't get them to touch. They kind of like start sliding past each other, right? Okay. So the key here is the closer 2 opposite charges are, the stronger the force between them. Now, up here, I wrote that this is the nucleus versus the electron. What color sphere would represent the nucleus? Why? It's positive. Now, the problem is that what 2 things are in the nucleus? Protons but what's the charge of a neutron? So it doesn't matter. Okay? And we obviously know that the blue one is going to be what? The electron. Okay? So the closer the 2 are together, the stronger the force between them. So this is just another fancy picture of kind of showing what's going on. What do you think that little glob of red spheres is? Okay, this is the nucleus, and these really bitty, tiny golden things are going to be your electrons. Okay, according to this picture, which electron do you think has the strongest force? Very good. Okay, so this one is going to be the strongest. All right, well, that makes it really easy. Which one's the weakest? Okay, this is going to be your weakest. And how does all this tie in? Okay, what does all this mean? But before we do that, let's look at, and don't freak out, I have good news. You don't have to do any math with this. I just want to look at a very basic concept to how did they figure this out? Because there's some math behind it. You're not going to have to calculate anything, but I just want to show you. You do not have this slide, but somewhere around the slides you were just working, just write this. Just write that formula. Again, you're never going to have to deal with it, but I want to talk about something that will make sense. No. Because honestly, it's pointless to do the math of it. I mean, you could figure out the force between 2 points, but it's not worth it. It's because if you can look at it qualitatively, which means basically describe it, it's just as effective. So first of all, what does the letter F do you think stand for? Force. So that's easy. Don't worry about K. That's some constant. But Q1 and Q2. What Q is the charge. And real quick, this will make sense. Just a few minutes ago, I showed you this one. You have positive Q and negative Q. So basically, you're talking about the protons and the electrons. They have a charge value. Okay, you can look those up. But the important part is this R. Okay, if you want to write R underneath, if you want to write that this is a distance, that may kind of help you make more sense of what I'm fixing to ask, but this will make sense. What we just said about Coulomb's law is the closer 2 objects are, what happens to the force? The stronger the force. So do you agree that we want a really high F? We want a really large F. Well, in a fraction format, if I want a really big, large F, what does that need to be? What does R need to look like? Really small. So if your distance is really, really small, mathematically, does it prove that f is going to be really large? If you're dividing by a tiny number, your value is going to be really large. So do you now want to understand what I mean when I say qualitatively you can describe it and it's just as effective as plugging the numbers in? It's useless to plug the numbers in, but you can compare it. Okay. The one last thing I want to point about this is what is going to happen between the top two spheres. Are they going to attract or repel? How can you tell? They're positive, negative, and then you've got positive, positive will push apart, and then negative, negative will also push apart. So again, the only thing I wanted to show you was just how the formula is true for the law that it represents. Okay, so kind of shifting gears, but kind of staying in the same area. Above this term, effective nuclear charge, here's what I want you to write. Zeph. Zeph. Now, I know what you're thinking. What the heck is Zeph? It's a good question. So let's talk about what Zeph is. First of all, do you know where the EFF comes from? Effective. Well, that's easy. So effective nuclear charge. So why do they use the acronym Zeph for effective nuclear charge? First of all, if you ever see the letter F for temperature, do you know that stands for Fahrenheit? If you ever see the letter H in calorimetry, what is that? The letter H. Enthalpy, very good. If you see the Greek symbol lambda, what is that? Wavelength, very good. So they chose Z for a reason. So let's talk about why they chose Z. Now, if you want to write this down, this is fine, but some of you may remember it, and you may not have to. Very good. So here's what this is. Here's why Zeph, the letter Z, was chosen. First of all, you know what X is. What is X? That's the element. Okay? Does anyone remember what A was? Okay, this is the mass number, and all that simply was protons plus neutrons. Okay, so as you're adding those numbers. But Z is the important part here. Z is the atomic number. Okay, and what does the atomic number also represent? Very good. The number of protons, and where are the protons? In the nucleus. So the number of protons in the nucleus. So now, we know that Z specifically refers to the number of protons in the nucleus. So when I go back, and I promise I'll come back to this in just a second if you didn't get it all. So if we go back and we look at effective nuclear charge, again, what is a charge? You're either looking at positive or negative. And what is the charge of the nucleus? It is positive because of the what? Protons. And what letter represents protons? Z. I see what you're saying. What letter represents the number of protons? Is the letter Z. And so, in a long story, that is why Zeph stands for effective nuclear charge. Does that make sense? Did I lose anyone going through that? Are you glad I did that? Makes more sense? Okay. So here's what effective nuclear charge is. How many of you don't like kids? Like they're the... All right, Grayson, you're the perfect example for this. Kind of wish Aubrey were here to hear this. I'm going to take you up to Slingloff, and I'm going to take you outside on the playground, and I'm going to send 20 kindergartners out there, and you are responsible for all of them. Do what? Pre-K, K. They are both awful little ankle biters. So, but we're going to stay with kindergartners just for the fair assessment up here. And Grayson, it is your job to maintain them from either killing each other and climbing over the fence and running away. That's a challenging task, right? So what we're going to call Grayson is the nucleus. He's the thing that's going to hold this whole chaotic thing together. Because let's face it, atoms are chaotic, right? Okay. What are electrons constantly doing around the atom? They're constantly moving. That's what kindergartners never stop doing. They never stop moving. So especially if you put them on a playground, they're going to be running everywhere. So what Grayson is the nucleus, and the kindergartners are the electrons. So his objective is to keep them from leaving and escaping. Because what do electrons potentially want to do from that atom? They potentially want to get away somehow, some way, but it's the nucleus's job to hold them in. And if you do a really good job, are you effective? So that's why it's effective. So how effective is the nucleus in holding those electrons in? It's its job to be effective. Now, what happens when you've got 20 of them out there and I send little Johnny out on the playground? Okay, well, obviously there's 21 of them, but Johnny's your problem child. He's going to do everything in his power to get away from you. So every electron we add, does it make it more challenging to hold it in? Yes. Okay. Well, what happens if you've got 20 of them out there and then I bring in little Susie because she hurt herself? Okay. Has your job become easier or harder? It's easier. So the less electrons we have, the more effective it is. The easier it is. Is that all making sense logically? Okay. Now, let's pretend that we sent you back out there with all 20, but you had 20 of your friends with you. That's really simple, right? You're man defense, and you are responsible for one person. So let's talk about that in terms of an atom. If you have an atom of, let's use carbon, okay? Because carbon's just an easy atom. There are 6 protons in carbon. Do you agree? Well, if it's a neutral atom, how many electrons do you have? 6. So you are 6 on 6. Are there any atoms that have 1 proton and a crap ton of electrons running around? No. They're all built and designed to be neutral. So which means it's just like the example. It's 20 on 20. You can do whatever it takes to make it as effective as possible. Okay? So that is what effective nuclear charge is. It's the nucleus's job to maintain all those electrons that are running around the atom. Ions, okay, and that's where this is going to kind of come into play later on down the road, and we're going to talk about, well, what happens if you add an electron. So let's pretend that it's 20 on 20, and I send little Johnny out. Well, now you have one person that's got to play zone. You've got to have one person playing 2 kids. So is it as effective as it is one-on-one? And that's how ions can work here. Okay, and so that's kind of a way. So if it was 20 on 20. Would the kids be able to go as far if it was 1 on 20? No, not near as far, okay? And so that's the way it works, but guess what happens? If it's just you out there by yourself, there's this term called electron shielding. So Johnny's got a little group of cronies that's going to help him out. So they're going to do everything they can to keep you from watching him. So they're going to tackle you and beat you up, bite your ankles like most kindergartners want to do. And, what they're going to do is they're going to try to keep you from paying attention to little Johnny. Well, what is another word from keep you paying attention? Shielding. Okay? So shielding is nothing more than blocking your view, right? So we've got this first ring of electrons, and notice what they are doing to keep the outer electrons from being pulled in. Because do you agree that there is a sense of attraction from the nucleus to those electrons? Someone tell me why they're being attracted. Positive and negative. Very good. Okay? But this ring right here, let me change the color. This ring right here is causing an issue. Because what else is going on at the same time as there's being attractive forces? And I know how that looks ridiculous. Sorry about all the colors. But why are there repulsion forces that are going on? They're both negative. Very good. So, this is why this is challenging. Yes, we've got the nucleus, Grayson, trying to keep little Johnny inside of his yard or in the atom. But as soon as he starts pulling him back in, guess who shows up to protect Johnny? The other electrons, that ring, that inside ring. So does electron shielding make sense? And I'm trying to make this as simple as possible, and I hope that I am. I'm using as many analogies as I can here. Yes, sir. Okay, so great question. Why aren't they like stuck to it like Velcro balls, if that makes sense? Okay, because the amount of energy that they have the ability to move, and the attractive forces. So that blue line is not strong enough to keep it pulled in close enough to keep it from moving, but it is close enough to keep it from just going everywhere. So it's kind of that midway thing that it's just enough, but not too much. Okay, it's kind of like you, like when your parents give you the freedom to go out on the weekends and just kind of make, but they trust you to do that. That's kind of the same thing with the nucleus. They trust them to do what they're supposed to do. Okay? Yes. They are. And as a matter of fact, that's a good point. So what he just said, since there is a sense of attraction here, we just talked about that distance thing. This electron right here, in the green circle versus the red circle. Nope, that's not red. Which electron, the green one or the red one, is more attracted to the nucleus? Why? It's closer. That's exactly what we just talked about in Coulomb's law. Yes, sir. Yes. And that's the part about this that no one understands, is that how does this all line up perfectly? This is why it's amazing that life even exists, is because all of this stuff works and we don't know how or why it works that way. We just have come up with these assumptions that have been proven mathematically. We just can't understand why the math works. But it is what it is. Can you overcharge something? I don't know if you're asking it the right way, but yes, there is a sense that you could have too many electrons. Okay. So we've already talked about this. We know that a quantum is a unit of energy that can be lost or gained by an atom. And again, if it's absorbed, you know that it's going to jump up energy levels. If it's emitted, you know that it's going to go down some energy levels. So that's just another picture of everything that we've talked about thus far. All right, how much time we got left? All right, we can do this. We're not going to cover any more like topics, but I do want to do this because it'll make sense tomorrow whenever you see this. So here's what I want you to do. It's really simple. It's just kind of common sense stuff. I want you to write this down in this particular order. We're going to do your address, but we're going to write it in a weird order. So the first thing I want you to write is the state that you live in. Write the abbreviation for it. Somewhere around this slide. Write the state that you live in. Abbreviate it. Hope it's all AL. Okay. Write the city that you live in. Yep. So AL, comma, city. And we'll put commas between all of them. And there's a reason I'm asking you to do it in this order. Okay. After the city, write your zip code. Okay. After your zip code, write your street name. Like what street do you live on? No, why? Well, there's a reason we're doing this. And the last thing is your house number. So like what is the on your mailbox? What's the number on your mailbox? All right. So let's start with the first thing. How many of you live in the state of Alabama? Hopefully all of you do. How many of you live in Dothan? Now, is there anyone that doesn't live in Dothan? There's a few. Midland City, Ashford. Chloe, Ashford? No, you're in Dothan? Any Midland City? Are you? Okay. I know there's a few, like, Dothan has incorporated a little bit of Midland City addresses, so I'll get that occasionally. All right, so let's start with zip codes. How many of you are 05? I'm 05. Okay. Are you kidding me? You're 03. Yeah, because 84 splits. You're 83. Highlands is 05. How many of you are 03? Most of you are 03. All right, is anybody 01? Okay. Is anybody 50? The Midland City. Yep, there's a Midland City. Okay. All right. The next one is street name. Does anyone in here live on the same street by chance? Cody, do y'all live on the same street? All right, well, there we go. All right, so we got two people. However, have we limited the chances of that happening? Yes, so we've got only two people that live on the same street. Now, we could talk for hours about this, and it would be hard to figure it out. But is it possible for someone to live on the same street as you and have the same house number? No, UPS, the Postal Service doesn't allow that. So what am I trying to get at? Is it possible for someone outside of your home, outside of your walls, to have the exact same mailing address as you? It is physically impossible. Now, are there main streets all over the country? But their city's different, the state's different, and possibly state, and definitely the zip code is all going to be different. So what does that matter? Why are we talking about all of those things? Because this bullet right here, put a big star beside that first bullet. In the same way that no two houses have the same address, this is going to apply to electrons, because electrons have addresses. But we don't call them their address. We call them quantum numbers. So when you hear the phrase quantum number, I'm referring to an electron's address, and it has 4 parts, just like yours. We have a house number, a street name, a city-state, and a zip code. So just like we have 4 parts, so do the electron's quantum numbers. And there's an acronym that we have for it, and it's PAM's quantum numbers. It's an acronym. P is, you don't have to write this down, but let me show you so you don't write all this down. We're going to get to it after all these things. We're going to come back to it right here. Don't find it. It's in there. I promise we'll get to it. It's principal, angular, magnetic, and spin. These are the 4 quantum numbers. And again, what does it refer to? An address. It's the address of those electrons.